Hello, welcome to Brilliant Academy. In today's class, you're going to learn how to use dimensional analysis to determine the correct relationship between two or more physical quantities. So let's say that velocity, displacement, and time is being given to you. How do you detect how they correctly relate to each other? We already know that velocity is equals to displacement all over time. So assuming you don't know, is there a possible means for you to detect or determine how these three variables relate to each other? The answer is yes. You can actually use dimensional analysis to detect how two or more physical quantity relate to each other. So let's say you are given wavelength, you are given period, you are given force, and you are asked how do they depend on each other. You can actually use dimensional analysis to do that. So let's quickly take one example to explain the concept and how to actually. So consider the equation you have on your screen. You can as well take them. We have that the speed of a ripple depends upon the wavelength, density, and surface tension of water. Using dimensional analysis, derive the exact form of their relationship. So we have that velocity depends on wavelength, and it depends on density. It also depends on surface tension. So putting these three parameters together, we have that velocity depends on wavelength. It also on depends on density, and it also depends on surface tension. They are represented with the following symbols. So the question is that using dimensional analysis, we should detect how these different physical quantities relate to each other. Now, please let me explain something. We have that velocity is equal to distance all over time. This is how it relates. So we can actually put this in a straight line equation. So we have that v is equal to t displacement multiplied by time to the power of minus 1. So this and this are still the same. So the concept is that these parameters are supposed to be written in this form. So they have powers. Let's call those powers x, y, and z, which determine how they relate. Like to this now, seeing that we have t to the power of minus 1, we know that we are dividing by t and we are not multiplying. So bringing that same concept here, this is how this is supposed to be written. So they have powers, but then we don't know the powers for now. Now, mathematically, we know that if we want to take out the proportionality sign, we introduce a constant. So we have that v is equal to k multiplied by the wavelength to the power of x multiplied by the density to the power of y multiplied by surface tension to the power of z. Now, please note, in every question that you are asked to derive the correct relationship, you are always going to be given the value for k. But if you are not given, just make the assumption that k is equal to 1 and you just have to take it off. So we have that v is equal to wavelength to the power of x multiplied by the density to the power of y multiplied by the surface tension to the power of z. Now, your ability to solve this question depends on if you know the dimension of these different physical quantities. I actually have a video. The link to that video is actually in the description of this current video you are watching. So you need to know the dimension of every physical quantity. If not, you cannot apply dimensional analysis in this question. So what we have to do now is to impute the dimension of these different physical quantities. So for velocity, we have the dimension to be L multiplied by T to the power of minus 1. This is equal to we put in the dimension of wavelength. Wavelength is actually distance. So what we are calculating for wavelength is distance. So the dimension is L to the power of x multiplied by, for density, we have the dimension as L to the power of minus 3 to the power of y multiplied by the dimension for surface tension is m multiplied by t to the power of minus 2. Now, why are we doing this? Let me explain the concept, and please do well to pay attention at this point. Please do well to pay attention, because if you don't understand the concept here, you are likely going to miss the idea, and you might just be solving, but then you've not gotten the concept. So the idea is that we have a principle called the principle of dimensional homogeneity, which says that for an equation to be correct, let's say for velocity, which is equal to displacement divided by time, it's actually the same thing. Now, the principle says that for this equation to be correct, it means that the dimension here is the same thing as the dimension here, and we can look critically at it. The dimension for velocity is L multiplied by t to the power of minus 1. The same thing to this part. If you simplify here, we have for distance is L multiplied for time, we have this to the power of minus 1, so t to the power of minus 1. So you can see that the dimension here is the same thing as the dimension here. So using this concept, we know that if this equation will be correct, if it is said to be correct, then the dimension we have here will be the same dimension we should have here. And now, looking at this, we have that for this distance is to the power of 1, while time is to the power of minus 1. So for these different variables, they have powers that we don't know. If this dimension is equal to this dimension, that means we can equate the powers here to the powers here to look for the values of x, y, sorry, we have z here, x, y, and z. Now, if we get the values of x, y, and z, we can now impute them here, so we can know how these three parameters relate to this. So assuming we finish solving and we have that z is equal to minus 1, it means that the correct relationship is v equals to lambda multiplied by density all over surface tension if we have z to be minus 1. So let's use the concept that if this equation is correct, the dimension here will be equal to the dimension here. Using that, so quickly, let's simplify what we have there. What we have there, we have that L multiplied to the power of t, L multiplied by t to the power of minus 1 is equal to, this is L to the power of x, so we have L to the power of x multiplied by, this is m, and we have y, so y, m to the power of y, so we have m to the power of y, and this, let me quickly explain what is here. So assuming I have a multiplied by b all to the power of n. This is equal to a to the power of n multiplied by b to the power of n. So what we have here is m to the power of y and l to the power of minus 3y multiplied by, same thing to this, we have m to the power of z multiplied by t to the power of minus 2z. Notice that we have n here, we have n here, and from indices, if we have the base to be the same, we can actually add up the powers. So let's just simplify what we have. We have m here, we have n here, we have l here, we have n here, so we can add up their powers. So we have l multiplied by t to the power of minus 1 equal to l. This is, we have n here, we have n here. Since everything is multiplying, we can take one of the l and add up the power. So we have x plus minus 3y. We have minus 3y multiplied by, for n, we have n, there is n here and there is n here, so we have y plus z. This, we are adding this and this multiplied by t to the power of minus 2z. And please always try to express them in the form MLT. So we are just going to do that. We have L multiplied by T to the power of minus 1 equals to MLT. We start with M to the power of y plus z multiplied by L to the power of x minus 3y multiplied by t to the power of minus 2 multiplied by z. Looking at the both side of the equation, we have m here, we have n here and we have n here. We have t here and we have t here. But we have n here and there is no m in this part of the equation. And the principle of dimensional homogeneity says that whatever is here will be here for this equation to be correct. So how do we try to amend the equation without destabilizing the real form of the equation? Notice that if I have 2 multiplied by 2, this is equal to 4. And if I have 2 multiplied by 2 multiplied by, let's say, 50 to the power of 0, this thing equals to 4. So if I add anything to the power of 0 into this, it doesn't change anything in the equation. So we can actually apply the same method here. So we can say that we want to bring in n here without destabilizing the equation. So we have that. So we can introduce m to say m to the power of 0 multiplied by L multiplied by T to the power of minus 1. This is equal to, then we bring down back our expression. We have m to the power of y plus z multiplied by L to the power of x minus 3y multiplied by T to the power of minus 2 multiplied by z. In the form to which we have written the equation now, we can now match, since we have m here, we have n here. From indices, if we have the same base at the two sides of the equation, we can equate their power. So what I mean is that if I have 2 raised to the power of x equals to 2 raised to the power of, let's say, 4, this means that x is equal to 4 from indices. So if we can equate this power, we can say that 0 is equal to y plus z. So we say that 0 is equal to y plus z. Let's call this equation 1. Notice that we are trying to get the value of y x, y, and z, so that we can impute it here to know how this different physical quantity relates to velocity. For L is actually raised to the power of 1, but no need to write that. So we have 1 equal to for L here, we have x minus 3y equals to x minus 3y. Let's call this equation 2. And for T, we have minus 1, and that's equals to minus 2 multiplied by z. So we have minus 1 equals to minus 2 multiplied by z. Let's call this equation 3. Then from equation 3, we can get the value of z. So making z subject of the equation here, we have that from equation 3. From equation 3, we can say that minus 1 is equal to minus 2z. We can divide both sides by a minus 2. So we have minus 2 here all over minus 2. This will cancel this. So we have that z is left here. We have that z is equal to minus 1 over minus 2. This equals to 1 all over 2. So we have the value for z equals to 1 all over 2. That 0 is equal to, we are actually solving them by either having these three equations. You can solve them simultaneously or by substitution method to find the value of x, y, and z. That's actually our main goal, so that we can find the relationship here. From here, we can impute the value of z here, so that we can find that of y. So we have that 0 is equals to y plus z or z. So we can take y to this part, so we can take z to this part of the equation. We have that z is equals to y minus z, minus z is equals to y, and z is equals to 1 over 2. So we have that minus 1 all over 2 is equal to y. So y is equals to minus 1 all over 2. So we've gotten the value for y, we've gotten the value for z. So let's see how we can get the value of x from this equation. So considering this equation, we have that 1 is equal to x minus 3y. But we know that y from here, y is minus 1 all over 2. So this is multiplied by minus 1 all over 2. This multiplied by this, we have plus. So we have this equals to x minus 3 multiplied by minus 1. We have plus 3 all over 2. So we can actually move this to this part of the equation. We have that 1 minus 3 all over 2 is equal to x. Therefore, x equals to 1 minus 3 all over 2, and this is equal to 1 all over 2. So we have that x is equals to minus 1 all over 2, y is equals to minus 1 all over 2. We have that z or z is equals to 1 all over 2. In this form to which we have written the equation, this is not actually the direct, the correct form. What we have is v is equal to wavelength to the power of x is given as minus 1 all over 2 multiplied by density to the power of y is minus 1 all over 2 multiplied by surface tension, which is to the power of z, which is 1 all over 2. Now, simplifying this further, we have that v is equal to, from this we can say that velocity is equal to, what we have here is 1 all over square root of the wavelength. So let me explain what I did here. So if I have 1 If I have a to the power of minus 1 all over 2, this is equal to 1 all over a to the power of 1 all over 2. And this is equal to whatever you have to the power of 1 all over 2, that's the square root. So we have that this is 1 all over square root of a. So the same thing I did here. So this is multiplied by what we have here. The same thing, we have that this is 1 all over square root of the wavelength multiplied by, this is just these ones, they have negative sign, but this doesn't have, so it's just square root of wavelength. So multiplying this together, we have that the velocity is equal to, multiplying this, we have that the square root of the wavelength all over this and this, multiplying this and this. So we have square root of lambda and surface tension. And this is equal to, if I have a square root of a all over square root of b, this is equal to square root of a all over b. So let's just apply the same concept here. So this is equal to square root of the surface tension of the water all over the wavelength multiplied by the density of the water. So V is equal to square root of surface tension all over the wavelength multiplied by the density. So this is actually how velocity relates to the physical quantity given to us in the equation. It's very often to find out that students find it hard to grasp the concept with just one example in trying to find the direct relationship. So let's see one other problem to solidify your understanding or comprehension towards the concept.